This video is about anti-differentiation and integration of vector-valued functions, or just vector functions if you prefer. And we're also going to discuss motion. So our vector functions are given by a parametric representation R of t. Let's say that we are in three-dimensional space. Everything holds in n dimensions, but if we're in 3 dimensions, R takes a real number t in the domain, and it's going to map it to a point, x of t, y of t, z of t. So maybe our curve looks like this in 3 dimensions. I always like to give it a lot of little loops. I think of a bee flying around or something like that. So we've got x here, y here, and z here. And our vector-valued function r of t starts at the origin. It points to a particular location. It says, there you are here at this location, perhaps at a particular time. Now t can represent things other than time, but often it represents time. So at this time we are at this position. With the interpretation of t as time, we can call r of t a position vector. It gives us a location, x of t, y of t, z of t, at a particular time. And that's why we call it a position vector. Then the last couple of videos we learned how to differentiate these. If I want the derivative of r prime, or if the derivative of r of t, all I have to do is take the derivative of each component. So I get y prime, or x prime, y prime, and z prime as the components of this derivative vector r prime. If I wanted to take the second derivative, we haven't talked about that yet, but you can guess. You just take the second derivative of each of the components. Now once you go beyond the third derivative, fourth derivative, fifth derivative, instead of using these primes, we don't write 5 primes in a row. We would put a little 5 in parentheses. That's not the 5th power, that's the 5th derivative. So this is the number of derivatives you're supposed to take. So the 5th derivative would be like this, would be written this way. In our prime notation. In general, the nth derivative is written this way. And sometimes people use superscripts and parentheses like this for something else, but most of the time, unless someone tells you otherwise, if they do this, they mean the nth derivative of that function with respect to whatever independent variable is there. So in this case it's t. Alright, so that's how we take derivatives. We take them over and over, we just do that. And guess how we take the antiderivative? It's pretty simple. If r of t has 3 components and you want the antiderivative, you just take the antiderivative component by component. So you take the antiderivative of x of t, multiply that by I hat. Take the antiderivative of y of t, multiply that by j hat. And then the antiderivative of z of t, and multiply that by k hat. And of course this works in 2 dimensions, it'll just look like this. In n dimensions you just have n components, but it's just like derivatives. You take the derivative component by component. With antiderivatives, you take the antiderivative component by component. Then we can also evaluate definite integrals. You might say, oh gosh, what does that mean? I'm taking this vector, I'm multiplying it by dt, and I'm integrating from a to b. What does that mean? Well, turns out you're going to get another vector. Its components are these. You just integrate each component. And when you integrate each component like this, remember, every definite integral is giving you a number. So the definite integral of a vector-valued function is giving you a specific vector. And the components of that vector are given by the integral of this, and the integral of this, and the integral of this. Now this one is a little different. We're still doing the same thing. We're anti-differentiating component by component, but we don't have any bounds here. So you're going to have a constant of integration for this one, and a constant of integration for this one, and a constant of integration for this one. So I usually call those C1, C2, and C3. But this is going to produce another vector valued function. This is producing a particular vector with particular components, and the components are given by those three numbers that we get when we do that integration. We're going to tend to use this whenever we're thinking of R as a position vector. So R is position. It gives you a particular position, x of t, y of t, z of t. At a particular time, t. So we're going from time t to a position, or I like to call it a location. It just helps me think of it the right way. If I call that x of t, y of t, z of t, that's my location. All right. Any guesses on what r prime of t represents? Remember when we took the derivative of a position function back in Calc 1? Let's write it down using Leibniz notation. It makes it a little bit easier to see. This is change in position per change in time, but it's instantaneous. What's the instantaneous change in position per unit time? I hope you said velocity, because that's correct. Change in position, that's displacement. So this is displacement per unit time instantaneously, at an instant. So if this is position, first derivative is velocity. Now it makes sense that when I compute r prime, it's tangent to the curve. If I'm right here, let's say I'm right there on my curve, and then I compute r prime and it's pointing this way, well, that's telling me my velocity is this. At this point in time, I'm going in this direction. I'm also turning a little bit, it looks like. But that's telling me the velocity with direction and its magnitude, and tells me my speed, and tells me which way I'm going. If I take the derivative again, so that's change in position per unit time per unit time. I hope you said that's acceleration. So you've done this before, but when you did this before, looks like that in Leibniz notation, your position function was in one direction only. So you might have the x position as a function of time. So back in Calc 1, you might have been a particle on a number line, and all you got to do was go back and forth on the x-axis. Like, oh, that's kind of interesting. Now we get to go anywhere we want in three-dimensional space. And our velocity, if this is our position function, our velocity is given by this vector. Our acceleration is given by this vector. You just take the derivatives twice. Do you remember jerk? Many people don't. Jerk is just the derivative of acceleration, so it's r triple prime. And you just take the third derivative of each of the components. Easy breezy. Now back in Calc 1, when we talked about speed, we said speed was the absolute value of velocity, but that's because our velocity was one-dimensional. It was just this x prime that was going back and forth on this line. We said if we're going in the positive x direction, let's call that velocity positive. If we're going in the negative x direction, let's call that velocity negative. And then we said the absolute value of that is the speed. It doesn't make sense to talk about absolute value of velocity anymore, because velocity is a vector now. Position is a vector, velocity is a vector, acceleration is a vector, jerk is a vector. All of these are vector quantities, and they're calculated by taking repeated derivatives of the components. Now if I want speed, I need the magnitude of velocity. And I apologize for the notation on behalf of math people everywhere. It looks like a V. It's sort of like a weird shaped V. That's a Greek letter nu. Speed is the magnitude of velocity. and velocity is r prime. So you're just going to take r, your position, take its derivative, that's giving you a velocity vector. The magnitude of that velocity is the speed, and this is represented by nu. And if this is a function of time, speed is also a function of time. Now notice, this is a vector, this is a vector, this is a vector, this is a vector. Speed is a magnitude. So speed is always positive except for when it's 0. So this is a scalar. Speed's a scalar, all the other three guys are vectors. Now that I know that, now that I know that r gives me position, r prime gives me velocity, r double prime gives me acceleration, jerk is r triple prime. You might think your teacher is a jerk for making you calculate r triple prime. I don't even know what letter we would use for that. I don't want to use J, we use it for something else. I'm just going to call it A prime. And speed is this lowercase nu as a function of t. It's the magnitude of the velocity, which is the magnitude of the derivative of position with respect to time. Now that we know this, we have this list, I can find one of these given the other guys almost, not completely. We're going to get constants of integration every time we anti-differentiate. So let's say I have position and I want velocity and acceleration and jerk. Well, I just take the derivative of position to get velocity, I take the derivative of velocity to get acceleration, I take derivative of acceleration to get jerk. If I want speed, after I've taken this r prime, I just take its magnitude, and that's my speed as a function of time. If I want to speed at a particular time, find its magnitude, and then I plug in the t value. So it's very simple. But if I gave you velocity and asked for acceleration, you take the derivative. Any ideas on how I would get from velocity back to position? If I'm trying to get rid of the derivative, I take the antiderivative. So let's write this down. If you're given velocity, you can find position by taking the antiderivative. So position is the antiderivative of velocity, or it's even more obvious if you see it as the antiderivative of the derivative. The antiderivative of the derivative is the original function. Unfortunately, this is going to have some arbitrary constants in it. I'm going to have one arbitrary constant for each component. That's not very useful. If I tell you, this is my position as a function of time, plus or minus as many units as you want in the x, y, and z direction, well, I didn't really give you much of a position, did I? We need to know some initial position in order to find r of t completely. This is just going to give me some functions of t with some arbitrary constants in them that indicate the position. We'd like to not have any arbitrary constants in our position function if possible. So if I was given v and I wanted to find r, to get from here to here, I anti-differentiate. To get from velocity to acceleration, I differentiate. If I give you acceleration and I want to find position, well, acceleration is the second derivative of position. So velocity, well, that's the antiderivative of acceleration. It's going to be r prime plus some constant of integration. I'm going to call it C1. And it's a vector C1. It's going to have components, as many components as r has. You say, okay, well, if we've got velocity, how do you find position? Well, position is the antiderivative of velocity. This velocity is this. And that's also going to have arbitrary constants in it. So if I give you velocity, we can anti-differentiate to find position and differentiate to find acceleration. If I give you acceleration, we can differentiate to find jerk, anti-differentiate to get velocity, anti-differentiate twice to get position. So you can go up and down this. As you're going down, you're taking more derivatives until you get to the speed that's different. So if I want to go from here to here, I just keep taking derivatives. If I want to go from here back up, I take an antiderivative. From here to here, I take an antiderivative. Or here to here, I take two antiderivatives. That's how it works. Unfortunately, though, we're going to have a lot of arbitrary constants in these answers. So we're not able to specify the complete answer unless somebody gives us an initial position or initial velocity to get rid of those constants. Now, when I quiz you over this material, I could give you any one of these and ask you to find the others. Keep that in mind. You might have to anti-differentiate twice to get position. You might have to differentiate to get acceleration and anti-differentiate to get position. But if I give you one of these, you can find all of the others. There might be some arbitrary constants unless I give you some initial conditions to specify those constants. So let's do an example of that. Now this is a bit contrived. I don't actually know of any function that has this as its velocity function. But this is good practice for us. Let's say our x component of the velocity is t squared times cosine of t cubed. And the y component of the velocity is just t to the fifth times, let's say, plus 4t. And the z component of the velocity is, say, natural log of t, and let's multiply that by t to the 1/2. If I give you this velocity function, and I ask you to find the acceleration, all we have to do is differentiate. So acceleration is the derivative of velocity, and I'm going to differentiate component by component. So I take the derivative of t squared times cosine of t cubed, and the derivative of t to the fifth plus 4t, and the derivative of t to the 1/2 times natural log of t, and that's giving me my acceleration. When you're doing this, you have to remember your derivative rules, product rule, quotient rule, chain rule, all of that from Calc 1, and you have to look at these and remember which rule is appropriate. Now this is not a product of three functions. This is a t squared times cosine of t cubed. We have to take the cosine of something. In this case, we're taking the cosine of t cubed. So this is a product rule when I take the derivative. I've got one function times another function, and that t cubed is inside the cosine, so I'm going to have to use the chain rule when I take the derivative of that guy. So let's just apply our rules from Calc 1. This is a good review. The derivative of a product is derivative of the first, which is 2t, times the second, undifferentiated, so leave it alone, plus the derivative of the second. Now this has got an inside function, so be careful. Derivative of cosine of something is negative sine, of that something, whatever it was you started with. In this case, we had a t cubed inside, times the derivative of the inside by the chain rule. Derivative of the inside is 3t squared. So that's derivative of the second times the first, undifferentiated. All of that is multiplied by t squared. Here I've just got a power rule and a constant times a t to the first. Derivative of t to the fifth, bring the power down, multiply by t to the 1 less power. 5 minus 1 is 4. If you have a constant times t, the derivative is just the constant. This I'm going to clean up in a little bit. I'll come back to that though. Over here, we're going to use the product rule again. We've got a first function and a second function. So according to the product rule, this is derivative of the first times the second plus derivative of the second. Derivative of natural log of t is 1 over t times the first. And we're done. It's just not simplified. So I've got 2t cosine of t cubed. And this 3t squared times that t squared is going to give me a 3t to the fourth. That's already simplified, so I'm just going to bring it down. Over here, I've got a t to the negative 1/2. You could put that in the denominator if you want to. I'm not going to. Here, it's an implied fraction. I subtract the exponents. 1/2 minus 1 is going to be negative 1/2. So this is plus t to the negative 1/2. So that's my acceleration. Now, if somebody gave me the same function and they said, given v and some initial position, so they say r of 0 is the vector 5 times I hat minus 3 times j hat. Actually, let's not plug in 0 because we've got a natural log of t there. Let's plug in 1. Let's not do 1 either. That's fine. That'll be fine. We'll do 1. It's going to be kind of ugly, but that's okay. So we'll do r of 1 is 5 times I hat minus 3 times j hat plus 2k hat, let's say. Okay? They might ask you to find r. Well, r is position, velocity is the derivative of position. So if I want to get r back, I need to take the antiderivative of velocity. Or you can think of it this way. You're taking the antiderivative of the derivative, and that's going to recover r partially. You're going to have constants of integration. These values, the 5, the negative 3, and the 2, are going to allow us to find the constants of integration. So we've got the integral of this guy, and that means you're going to take the antiderivative component by component. And I said this was contrived. I wasn't kidding. Just wanted us to get some practice with those critical rules. We need to remember how to do U substitution, basic rules, integration by parts, and all of that. Especially as we're getting you guys ready for differential equations next semester. So r of t is equal to this. Now I want to anti-differentiate this one, and this one. I don't want to do that inline. I think I'm just going to do them separately. So I'll anti-differentiate the x component first. So I had the antiderivative of, for the x component, t squared times cosine of t cubed. Is that integration by parts or U substitution? I notice I've got a product, so I'm thinking it's one of those. I definitely don't have a basic rule for that. I hope you said U substitution, and I'll tell you why. U substitution works. With U substitution, I'm looking for a function nested inside another function. So it's usually in parentheses. It's under a radical. It's inside a trig function or inside an exponential function. But it's something nested inside another function. In this case, we've got a t cubed inside the cosine function. So if this is a U substitution, chances are that's my inside function, that's going to be my U. So I take the derivative of that. Derivative of t cubed is 3t squared. Don't forget to multiply by dt to get du. And I'm not worried about the 3. I look at the t squared dt and I say to myself, is the t squared dt a factor up here in your integral? And it is. There's a t squared dt. So we're going to be able to write everything here in terms of u. It's going to be just fine. It doesn't have a 3 though, so I'm going to divide both sides by 3 to get the t squared dt by itself. And then this becomes this new integral. I've got cosine of my t cubed, that was u. The t squared dt, according to this, that's 1/3 du. I'm going to put the 1/3 over here, the du on the far right. And now we just anti-differentiate. Antiderivative of cosine is sine. I'm going to say plus c1 because I've got 3 components and each one of them is going to have a constant of integration in it. So I've got 1/3 sine of u plus c1 and u was t cubed. So sub that in. All right. So that's our x component. Our y component was a little easier. It was just a polynomial. We had t to the 5th plus 4t. You're just going to use a power rule here and a power rule here. Remember what we do. If there's a constant out front, you'd bring it down. It's just a 1, so we don't. Then we add 1 to the exponent and divide by the new exponent. Or multiply by 1 over the exponent, same thing. So I get t to the 6th over 6, or t to the 6th times 1/6. Then I bring the 4 down. There's an implied 1 there. Add 1 to the exponent. Whoops. Divide by the new exponent. Don't forget your constant of integration. We've already used c1. Let's call this one c2. So that's our y component. And then our z component is the antiderivative of, I think I had t to the 1/2 and natural log of t dt. Is that a u sub or integration by parts? I hope you said integration by parts. There's only one function inside another function here, and that's t. If I said let u equal t, well, that would just change all the t's into u's, and it would be in exactly the same place that we are now. So there's no function inside another function here. There's no fraction. There's no natural choice for u. So I'm thinking integration by parts is the way to go. Now remember, whenever you do integration by parts, if there's a log function or if there's an inverse trig function, that's your u. Otherwise, usually if there's a polynomial involved, u is usually the polynomial in that case. But this time we've got a log, so that's our u. And then remember, with integration by parts, dv is everything else. So u is natural log of t. I'm going to set up my little table. dv is the t to the 1/2 times dt. You want to differentiate to get u. Don't forget to multiply by dt. And anti-differentiate to get v. The derivative of natural log of t is 1 over t. The antiderivative of this, we use the power rule. So add 1 to the exponent. 1 plus 1/2, that's 2 over 2 plus 1 over 2 is 3 over 2. And then we divide by the new exponent. Dividing by a fraction is multiplying by the reciprocal. So we're going to divide by 3 over 2, which is multiplying by 2 over 3. We don't need a constant of integration when we're doing integration by parts. Then according to the formula, the integral of u dv is u times v minus the integral of v du. So we get this times this, minus the integral of v du. Now I cannot tell you how many students will anti-differentiate this and anti-differentiate that, call it a natural log, and then just multiply them together. That's not how this works. You have to simplify that first. There is no product rule for antiderivatives. You can't just do the antiderivative of one and the other and then multiply them together. It's not legal. So you've got to do something else. So I'm going to think of that as itself over 1 and that as 1 over t to the 1st. If we multiply straight across, we've got a t to the 3/2 over t. We can simplify that. You subtract the exponents, or you can think of like taking t to the 1st away from that t to the 3/2, and you get t to the 1/2. So simplify that. So this is equal to this down here. add 1 to the exponent, divide by the new exponent. Dividing by a fraction is multiplying by the reciprocal. Don't forget your constant of integration. We had a C1 and a C2, now we have a C3. Okay. That was a lot of work, but it was a good review of all those skills that we're going to need later in this course and also in differential equations. Remember what we were doing. We're trying to find R. R has an x component, a y component, and a z component. So we got 1/3 sine of t cubed plus c1 as our x component. 1/6 t to the 6th plus 2 times t squared plus c2 as our y component. And then all of this guy, that's our z component. Now this is not a very good position function, and you might say, it's because it's so contrived, and you might be right. But there's another reason why it's not a good position function. It's not a good position function because it has arbitrary constants in it. If I say, what's my position at time t equals 5 seconds, and you plug in 5 over here, you say, well, your x position is this plus a constant, and your y position is this plus some arbitrary constant, and your z position is this plus a constant. Those plus a constants make a big difference. It's not telling me a position at all. So I need to specify those constants, and we can specify those constants because somebody gave us more information. They had to tell us where we started in order for us to have a function without any arbitrary constants in it. So let's look at what they gave us. They gave us. It's what I gave you. It's okay. Let's be honest with ourselves. Okay. This says at time t equals 1, the position is 5 times I hat minus 3 times j hat plus 2 times k hat. I'm going to write that in my component form notation. So we were given r of 1 is 5 times I hat minus 3 times j hat plus 2 times k hat. And I want to use this to find C1, C2, and C3. That's easy enough. If you plug in 1 for t here, the x value is supposed to be 5. And when you plug in 1 for t here, the y value is supposed to be -3. And when you plug in 1 for t over here, the z value is supposed to be 2. So we can replace t with 1. So we've got 1/3 sine of 1 plus c1. And then if t is 1 here, we've got 1/6 plus 2 plus c2. If t is 1 here, natural log of 1 is 0. So this guy is gone. And we've got -4/9. The square root of 1 cubed is just 1 plus c3. And we're setting that equal to the vector with components 5, -3, and 2. So how does that work? Now remember, two vectors are equal if and only if their components are equal. So this has to equal this, and this has to equal this. And this one has to equal this one. And then you can just solve for C1, C2, and C3. So I've got 1/3 sine of 1 plus C1 equals 5. So C1 equals 5 minus 1/3 sine of 1. I know that's ugly, it doesn't simplify nicely. Sine of 1, it's a fine number. It's just some real number between -1 and 1, but I don't know what it is. It's not a special angle. So we're good. We're done with that one. And then for this y component, I've got 1/6 plus 2, so it's going to be 13/6 plus C2. That has to equal -3. Or if you prefer, you can call that -18/6. So C2 is -18/6 minus 13/6. So what's that, -31/6? That's our C2. And then for C3, we get this number, -4/9 plus C3. That z component has to be equal to 2. So C3 must be 2 plus 4/9, or 18/9 plus 4/9, or 22/9. Okay? So now you've got your constants. You are not done yet. You were asked for position, and you got so close to giving me a position, but you didn't give me a very good position because it had these arbitrary constants in it. We use this initial condition, that's what this is called. So it's telling us at time t equals 1, this is your position. We use that to find the constants. We are not done finding r of t until we substitute those constants. So substitute C1, C2, and C3 here to get r of t back. All right, almost done. This one's really long looking. Might even use standard unit vectors to write it because it's so long. So r of t is equal to 1/3 sine of t cubed plus C1, and C1 turned out to be 5 minus 1/3 sine of 1. All of this is multiplied by I hat. So this is just me substituting in C1. Then we've got our y component. So we had 1/6 t to the 6th plus 2t squared plus C2, and C2 happened to be negative 31/6. So we'll just subtract 31/6 instead of adding it. That's times j hat. And then we've got our z component, which is 2/3 t to the 3/2 natural log of t minus 4/9 t to the 3/2 plus C3 times k hat. And C3 turned out to be 22/9. This is our position. Now you know. They gave us the velocity, and they gave us an initial position, or they said when t equals 1, this is your position. And we were able to completely recover the position by anti-differentiating, plugging in 1 and solving for the c's, and then back substituting. Now if you give me any time, you say t equals 10 seconds, t equals 5 seconds, we can plug that in, and this will give us our position. Last question. Somebody might say, what is the speed? And you could find the speed as a function of t. Remember, that's just the magnitude of the velocity. And you were actually given the velocity vector. Long time ago, the velocity vector was given to be this, t squared times cosine of t cubed times I hat, plus t to the 5th plus 4t times j hat, plus t to the 1/2 times natural log of t times k hat. And you want the magnitude of that guy. So just remember how we find magnitude. You take the components, you square them, you add them, and take the square root. So I've got my x component squared, and my y component squared, and my z component squared. This is the product of two factors. I can easily simplify this, so I will. That's t to the 4th cosine squared of t cubed. This one, I could write it twice in FOIL, but I don't think that's going to make it any simpler, so I'll just leave it alone. You could square these. Square root of t squared is going to be just t, provided t is positive. Well, t has to be positive because we're taking square root of it, right? Positive or 0, so that's good. And then we've got natural log of t squared, so we can write it as natural log squared t. It means the same thing. This is our speed. Now if you give me a time, say time t equals 1, I can tell you what the speed is. Time t equals 5, I can tell you what the speed is. Okay, so just a refresher. Given one of these, we can find all the others. I have acceleration and I want position. I just anti-differentiate twice. Now I'm going to need an initial velocity to get the complete velocity, and I would need an initial position to get the complete position. But otherwise, we could find the position. It would just have a bunch of arbitrary constants in it. If I want to go from here down, I take derivatives. If I want to go from here up, I take antiderivatives. Speed is the only scalar on this list. The other three, or the other four functions, these are all vector functions. So position is a vector, velocity is a vector, acceleration and jerk are now vectors. But speed is still a scalar, and it's a non-negative scalar. It's always positive except for when it's 0.